This is actually a talk. I even gave you a bonus slide that just presented at the International Council of the Aeronautical Sciences in Florence. So all these things are on NTRS along with the full length paper. If you really want to go to sleep at night and want to read that. So, okay. So I like to start off with a bit of a motivation here. So this is a talk about electrified aircraft propulsion, and there's been another propulsion revolution in aviation that occurred many, many decades ago, and that was when we started putting jet engines on airplanes. So I like to start with these two airplanes. They're both made by the same manufacturer, Bell Aircraft Corporation. On the left is the Bell P-63 King Cobra. It was the latest evolution of the 400-mile-an-hour fighters. These are both made in 1942, by the way, or first flights in 1942. It's an evolution of the Bell P-39 Aero-Cobra. So it's kind of the latest in technology, laminar flow wing, two-stage supercharger, all of the things, fixed a lot of the issues associated with the P-39. A very, very much a formidable fighter. We gave most of them to Russians, actually, under Lend-Lease. On the right side is the Bell P-59A Aerocomet. This was our first production jet fighter before the Lockheed P-80. So we wanted to see what it would be like to put a jet engine into aircraft. And one thing that you might notice is that both of these airplanes look pretty much the same, made by the same manufacturer about the same time. What happens if you take a piston engine out and you put a jet engine in? And this is what happened. So they flew within about 3 months of each other. You got about 3 miles an hour more of top speed, a few thousand more feet of service ceiling. You took 3 times as much fuel to go 80% of the range. So imagine that this is your advertisement for jet fighters. Do you want one? Yet, within a decade, or about a decade from this moment, jet fighters were dominating in Korea, and nobody makes piston engine fighter aircraft anymore. And the reason is that, yes, there were some significant drawbacks to the jet engine when compared to the piston engine, but we figured out how to minimize those drawbacks and take advantage of some of its good characteristics, things like its lack of thrust laps with speed, or lower thrust laps with speed, or change in thrust laps behavior with speed being a big one, to enable aircraft to go a whole lot faster at higher altitudes. And this is kind of the lesson of when we're talking about a revolution in aircraft propulsion. If you just swap out the engine, you're probably not doing good enough, and you're going to leave a lot on the table. So let's talk about electric aircraft and some of the things that are good about why electric aircraft are even entering the conversation. So one thing is an electric motor itself, when you compare the stored energy that goes into it to the shaft power that comes out, is very, very high efficiency, tend to be over 90% with modern designs. And you compare that to things like combustion engines, particularly at smaller scales. That might be as low as 20%. That might be as high as about 50%, depending on the engine technology and the scale that you are at. So right away, you're taking more stored energy, if it's in the right form, and turning it into shaft power at better efficiency. This comes without power laps. So since you're not combusting anything, you don't need air. Whether you're at sea level or you're at 60,000 feet, you get the same amount of power out of an electric motor. And there's always asterisks here associated with cooling and other sorts of little elements here, but well, take a little bit of license. They have very high power to weight ratios, and by the way, that high efficiency and power to weight ratio are kind of scale invariant. So at 100 kilowatts versus 500 kilowatts versus a megawatt, you can get about similar values-ish for efficiency and power to weight ratio. That's a lot harder with combustion. Thermodynamics likes big things. And because of all of these and other features, you got a single moving part a lot of times. You have this potential for some pretty high reliability, for pretty low noise with no exhaust and other sorts of elements, like a lot of torque at low speeds, and then without any localized emissions. And so if you're trying to do things like getting close to people, that's important. So what's the problem here? Why aren't we all flying them? Well, as it turns out, it's that stored energy that's a little bit of a problem. I think jet fuel is around 12 kilowatt hours per kilogram. The batteries we use for X-57, fully burdened with packaging and everything else, were closer to a more modest 150 watt hours per kilogram. So there is a very significant change in terms of the energy storage. Now, that was circa 2015. We're about double that now in terms of what we can do for aviation grade batteries, but that's still a huge hill to climb. You're talking a factor of 50 or 60 compared to what you can get out of good old jet fuel. There's a lot of airports. There's a lot of ground infrastructure associated with making sure transportation systems can get fuel. It's a bit more of a challenge for electricity right now. And those, that high efficiency means that a few of the other elements associated with the propulsion system means that you end up with these lower temperature components. Lower temperature, or one good thing about exhaust is high temperature and a great way to get heat out of the system. You have a lot of low temperature components now that have low temperature limits. Cooling these systems can be a challenge even at that high efficiency. And we just haven't flown them much. And certification is about how stuff breaks, not necessarily about how stuff works. So you have to learn how it breaks. And so certification can be challenging. So the opportunities that we see here are for are in places with a shorter range, higher frequency operations with smaller aircraft, really trying to blunt that mass of the energy storage system offset. If you don't need a whole lot of range, you don't need all of that fuel with you, but you're really worried about things like operating cost, and operating cost tends to be tied to reliability and energy cost, amongst other things, then there might be a lot of good opportunities for electrified aircraft in that space. If you're getting in close to people and you don't want to have local emissions, you don't want to have a lot of noise, electrified can really help you, which is one of the reasons why electric vertical takeoff and landing is something that so many folks are interested in. What we'll talk about here for the rest of this is we're going to look more at conventional takeoff and landing and focus on two areas that we explored with X-57's design, which is distributed propulsion. You'll notice there's a whole lot of spinny things on there compared to traditional airplanes. And then purpose-focused propulsors. We actually have a full-scale mock-up here. Thank you, Bird. The 3D printed version of our so-called high-lift propellers. And I said, this is full scale. The whole point of these was to only be used during takeoff and landing to lower the stall speed of our otherwise highly loaded wing. Otherwise, they were shut off and not used. And when you have something that is easier to integrate, like an electric motor that has a very high power to weight ratio, the penalty of carrying those extra propulsive systems that you only use for takeoff and landing is much lower. All right. So I've already taken way longer than my normal version of this talk, but when I gave this talk originally, I had about 18 minutes. So it's nice to have a little more time, give a little more color. Let's talk about X-57. Some of you may have heard of it. Some of you may not have. So this was a flight demonstrator concept for distributed electric propulsion. It wasn't always called X-57. It started off, we officially started in FY15 as the Convergent Electric Propulsion Technology, or CEPT. Later on, I won't give you the tortured acronym, that was called SEPTR. And then we got our X designation in 2016, and we're X-57. So you might see CEPT or SEPTR in some of our early works if you're ever looking it up, but it's all X-57. And like all X planes, the goal isn't to make a production aircraft. The goal is to learn things. And so we don't mass produce X-15s or X-29s, but those were sure useful for learning about things like high-speed flight in digital fly-by-wire and aeroelastic tailoring. And so similarly, we're trying to learn those lessons from X-57 in the most affordable and effective way possible. So really, the product of an X-plane is paper, and that's what we intended to get from X-57. And what was a little different about X-57 is we used several different design spirals or mods. We didn't actually start with an X-plane at all. We started with, in production, twin-engine general aviation airplane built by an Italian company called Tecnam. This is a Tecnam P2006T. It has 200 horsepower gasoline engines that are normally aspirated and can carry up to about 4 people and can go about, can cruise at about 140-ish knots. The first thing we did was we made a P-59 out of it. We took the gasoline motors out. We put electric motors in. We took out the gas tanks. We put in 850 pounds of batteries and battery management system into the back seat, which had the same amount of energy as about a gallon and a half of gasoline. And we use this really as a risk reduction for our bespoke electric propulsion system that we ended up needing to develop rather than buy off the shelf. We also, of course, learned what's just the impact of electrification. What's taking a P63 to a P59? What is that impact from that? The next thing, and these two I really consider the same. The project changed a few times where these were the same, they weren't the same. But this is where distributed propulsion comes in, where we put on this very highly loaded wing. And we'll talk a little bit in a moment as to why. So that, and the reason you put on this highly loaded wing is so you get better cruise efficiency. So you get better cruise efficiency. We put our big cruise motors out on the wingtips for favorable interaction with the wingtip vortex for even more efficiency. And then that, of course, really increases the stall speed compared to the baseline aircraft. So that's what Mod 4 does, is we put 12 high-lift propeller systems in front and we get our stall speed back by, at low speeds, blowing air over the wing. So we can again fly at the same speeds as the original aircraft. And the neat thing about this approach, again, not saying that anybody wants to go out and build mods 2 through 4, but as you learn things about these different modifications along every step of the way. What's it like when you just electrify? What's it like in cruise for this high speed wing? And can we recover that low speed performance? Do we get better handling qualities? I really like to show this chart to show the differences between the stock Tecnam and also Mod 2, which are the same airframes, as well as then Mod 3, 4, which is the highly loaded wing. So here we have the stock Tecnam aircraft. You can see the wing plan form here in particular. And one challenge in particular with smaller aircraft is they have a whole lot of wing area. And the reason that they have that much wing area and have a much lower loaded wing than, say, jet aircraft is because they tend to need to land in shorter fields than, say, your typical jetliners are taking off and landing from. So you want to be able to give them that capability, but the high lift devices that are available to you at this scale aren't going to be very effective either in terms of cost or in terms of performance, or sometimes both. So there's no substitute for wing area, so that's what you do. You have a big wing, and we'll see the impact of that big wing in a little bit. We put a very small wing on it. We go to 42% of the wing area. We would have loved to have kept them the same weight. In a perfect experiment, we would have. Batteries are heavy, and they were even heavier in 2015. So we had to increase the gross weight a little bit to be able to do this. So it's not a perfect comparison, but pretty close. You'll notice it's a much higher aspect ratio, but actually slightly lower span. And if you are studying aerodynamics, you'll know that induced drag goes with span loading, not with aspect ratio. So you actually have a slightly higher induced drag, both because of the higher weight and the slightly reduced span of this aircraft. You can see those propellers out on the wingtips. And again, those we move them all the way out to the wingtips because when you're in lifting flight, you generate a wingtip vortex, and we spin these propellers in the opposite direction. We can squeeze a little more aero-propulsive efficiency out of them. So what does this do? So what I'm showing here is that the black curve is really the stock Tecnam, so Mod 1 and Mod 2, and then the blue curve is Mod 3, and really is the same as Mod 4 in the cruise configuration. And we're showing the power off lift to drag ratio at 8,000 feet on a standard day. The reason this is important is if you remember back to your aircraft performance class, you might remember the Breguet range equation, which says how far can you go for a given amount of energy in a given airplane. And one thing that's really interesting about propeller-driven aircraft is that the velocity does not appear in that equation. It basically states that your range is a function of lift to drag ratio. You can think of this as your aerodynamic efficiency, as well as then your engine efficiency and other things. So what that really means is if you want your most efficient cruise in a propeller-driven aircraft, you want to fly at the maximum lift to drag ratio, all other things being equal. So that stock Technam has a maximum lift to drag ratio about the same as our airplane, as Mod 3 does. It's just that it occurs about 35 knots slower. And here it is. I've just bought my $500,000 twin engine airplane. I don't really want to go cruise at 80, 85 knots. I want to get someplace kind of fast. And this is the impact of having that big wing. Is yes, they will cruise at 140 knots, and in doing so, they lose 1/3 of their range because they are flying well beyond the maximum lift to drag ratio of the airplane. In fact, we actually wanted an even smaller wing. I think I saw Bill Fredericks on the line here. Our original, if you look back to the Leap Tech experiments, we had an even more highly loaded wing. It's just that you couldn't actually fit anything into it for flight, like structure or cables or other sorts of elements. That put it in perspective, even on the X-57, I think the maximum thickness was about 4.5 inches compared to close to 10 for the stock aircraft. So that's a lot of structural depth implications and sorts of things. And we had picked sort of an arbitrary cruise target of 150 knots. You'll see that come up as our high-speed cruise target. But you can see that there's a pretty significant difference in the lift-to-drag ratio, the aerodynamic efficiency, where you want to cruise. So why the wingtip props? And that's because, as it turns out, when you spin propellers, they change the lift-to-drag ratio of the airplane a little bit. And when they're in the position where the Technam props are, and there's a lot of good reasons why they put their propellers where they are, it increases scrubbing drag over the wing, it changes the lift distribution over the wing, and it further reduces the lift-to-drag ratio. By putting those props out on the wingtips, you have less scrubbing drag because only half as much of the wing is now exposed. We're changing the induced drag because we have, because again, we're fighting the wingtip vortex, so some sort of beneficial interference. And as you might expect, yes, at lower speeds, you get even more wingtip benefit. But even at that high speed cruise target, you see you're comparing about a 3% gain to close to a 10% loss. So what used to be an installation loss becomes a small installation benefit at cruise. And so that's why we're doing it. So what does it look like here? And I should also note, and I should have noted in the very beginning, so X-57, other than the stock version of it, the Mod 1 version did not fly. So we got through a lot of ground testing of Mod 2. The project actually just recently sunset at the end of March 24. We can talk about all of the reasons as to why, but I can state that it is not a fundamental issue with the technology. As it turns out, I believe one of my favorite lines from The Right Stuff is "No bucks, no Buck Rogers." So it took longer. We ran into some challenges. We ended up having to do a lot more subsystem development. This probably is very familiar to a lot of people in this room on whatever project you've worked on. And eventually, it's a zero-sum game. If we keep asking for more money, then other things have to stop, and then you guys get mad at us. So now it's your time to shine. So these are all performance estimates that we have from a lot of good models, but that we intended to back up with flight data. As it turns out, physics has worked for flight for a while before. It probably will continue to do so. So we're pretty confident in these estimates, but they are not backed by flight data. So a few things here that ends up happening. So we were a little bit heavier. So you'd expect to use more energy in cruise because of that, more induced drag. We had a slightly smaller diameter propeller, which meant that the propeller itself on Mod 2 was a little less efficient. And that's because we wanted to do the crazy thing of moving it out to the wingtip. And you can imagine that things like crosswind landing become really interesting and challenging when you have a propeller out on your wingtip. So we wanted to have a smaller diameter prop. That just means it's going to be a little bit less efficient. And yet, in spite of all of this, the engine itself was about 3 times as efficient. And so when I look across the flight envelope here, I see that Mod 2 was generally about 2.6 to 2.9 times more efficient than the stock aircraft. A couple other things I'll point out that are kind of interesting here. Let's see if I can get my mouse to work. So this line here is VH for both aircraft. So the Mod 2 is red and black for Mod 1. VH is the maximum level flight speed. In this case, I think that's at peak power, not at maximum continuous power. So one thing you'll notice is that as you go higher in altitude, VH for Mod 1 drops off. This is the impact of power lapse with altitude. At 8,000 feet, you're only making about 75% power because there's less air. Mod 2, it's making 72 kilowatts from sea level all the way up to 100,000 feet if you wanted to. So so what you're seeing there is the impact of power lapse to the point where our 150 knot cruise target, the stock airplane couldn't even meet it, not at 8,000 feet. So we had to kind of extrapolate to get that energy use ratio. What does this look like then in Mod 3? And again, Mod 3 is Mod 4 in the cruise configuration, so you can kind of think of them as the same. So this is what happens when we reduce that reference wing area. So we have a much more highly loaded wing. We have lower wetted area, so that's also going to contribute to less parasite drag. And then we have that wingtip propeller benefit. And so this is then the ratio of energy used in Mod 1. And the way we got energy in Mod 1 was looking at fuel flow and the lower heating value of the fuel, should have referenced that, compared to the energy being consumed out of the batteries in Mods 2, 3, and 4. And so we got very close to 5. We got about 4.8 was our last estimate for amount of for the ratio of energy used in Mod 3, 4 versus Mod 1. Our project initially kind of started with this sort of DARPA hard goal of 5 times as efficient. So hey, we round there. That's pretty good to a significant figure. So we felt pretty good about this in terms of many years later being able to hit that. Couple of other interesting changes here between gasoline, normally aspirated gasoline, and electric aircraft. So what is still my too long introduction, so I apologize for that. One of the things that we mentioned is work on airworthiness standards. I'm actually going to go out next week and present these charts to a committee working on airworthiness standards. And this is one of the challenges with the current airworthiness rules, in particular for small airplanes. Right now, for smaller airplanes, the only place where you have to define climb gradient is right here at sea level on a standard day. This here is at, I think this is at max continuous power, but might be peak power. I can't remember when I made this chart. So that's where you establish your climb gradient. There's a climb gradient requirement of 8.3%. And the reason they do this is they know you're going to operate it not at sea level, but they assume you're going to be normally aspirated. So they think that gives you enough performance at high and hot days. So as you go higher or you go hotter, air density gets less and you have a power lapse. With an electric motor driving a prop, the only thing lapsing is the propeller. So you get a much reduced thrust lapse with changes in density. And you can see now where even our heavier, slightly less powerful Mod 2 could have a better climb rate than Mod 1, at where we cross over here on a hot day at about 5,500 feet on a hot day. So those are, some places where we're flagging that we might need to consider changes in the airworthiness regulations for electrified aircraft with things like climb gradient. Now, bigger aircraft, you have to consider a lot of combinations of altitude and such, so they don't run into this same airworthiness challenge, but it's definitely worth mentioning here. This is my bonus chart. So I did have to, just for completeness, here's what rate of climb looks like between Mods 2 and Mod 3. So now these are both electric. They're both normally aspirated. They're both they have no power lapse with altitude. And this is what happens when you shift that L over D curve. So as you might expect, your best rate of climb speed shifts to a higher speed. And that's really about it. Last thing you might notice is this is where you start, and this is again only at max continuous, but that VH line, and you'll see it on the next chart, you'll see that that sure enough, Mod 3, 4 can go faster on the same amount of power. So last one I like to overlay here is what do the different flight envelopes look like across all of the different mods here. So it's a bit of a mess, but if you squint at it long enough, you either go cross-eyed or there's a couple of neat features that'll jump out at you. So number one, we'll start here on the left side, the stall speeds. So this is the stall speed of the stock Technum, and then Mod 2 would increase slightly just because of an increase in weight. That was it. This is only just the adjustment in weight. Otherwise, they're the exact same. Mod 3, if you don't put those high lift propellers on, you have a pretty dramatic increase in stall speed, and then in Mod 4, we get that back. In fact, I actually think had we tested this in flight, we would have gotten an even lower stall speed. This was a conservative estimate. We put a 10% margin on our high lift props in terms of the thrust output. because, well, this was the system under test, so we wanted to throw a lot of margin in there. And in fact, if you look at concepts like Electra.Aero has a very similar concept. They even visited here not too long ago. And in chatting with them, they said things like, we don't know the stall speed of this airplane yet because we get to over 30 degrees nose up and then the pilot gets scared. Or it's probably more the engineers get scared. And he says, at this point, the pitot data, is kind of not really giving us anything anymore. So sure enough, we can recover that low end of the flight envelope with distributed propulsion. In this case, these high lift propellers. The other thing you can see that I've already highlighted the difference here between what happens with normally aspirated to no power lapse. And if you kind of follow these lines to the lines of calibrated airspeed here, you'll note that this lapse isn't very much with altitude. So typically your service ceiling for a normally aspirated airplane is going to be set by your rate of climb. I think when we were looking at this, especially for Mod 3.4, our rate of climb ceiling was at about 50,000 feet. So we're really limited by the length of extension cord at that point because we had run out of batteries long beforehand. But that goes to show that other things come and limit our ceilings. So we had a ceiling of 14,000 feet that was set by supplemental oxygen requirements, as opposed to by performance requirements. Another interesting thing, if you're an airplane nerd like I am, is you take a look here. This is the never exceed speed. On the stock Tecnam, there's a nice big difference between the two. So this is usually set by, or never exceed speed is usually set by the design dive speed minus a little bit of margin. We kept it the same on X-57 because we didn't necessarily know if it was set by the tail or the window blowing in or something else. It's not always just set by the wing. So we kept the same never exceed speed, which was probably too low. But you can see what starts happening when you start to move to these highly loaded configurations. All of a sudden, VH and VNE are very close to each other. So if I'm starting to think about things like upsets at altitude, normally you have a lot of difference between the two at altitude, but I'm going to have a whole lot less difference with my highly loaded airplane. So little things to think about if you start designing distributed electric propulsion airplanes because you've been so inspired today. So I think I've kind of highlighted all of these elements, but so you always have to end with a summary slide here. So, just really what was interesting about compiling the data from this is a paper I've wanted to write for close to a half a decade, and we finally had time to do it, which was, what is it that, what's this impact of electrified propulsion? What's the impact of the highly loaded wing? And then we didn't talk about it a whole lot here, but we had a series of flight experiments in Mod 4, which was looking at things like what is stall speed, and do we recover the same handling qualities with stall speed? There's another older paper we have that talks about this, and we experienced this a little bit in the piloted sim that we used out at Armstrong. But a really interesting impact of using thrust for high lift is when you're on approach to landing. If you do it right, you have a speed stable airplane. There's no backside of the power curve or no apparent backside of the power curve to the pilot. So I think this is something that could actually dramatically increase safety for small airplanes if you get a little slow. We talked through the cruise benefits here on why we in terms of there's the benefit of electrification, and there's the benefit of the highly loaded wing and distribution, and of course, the importance of that of the difference in the lapse capabilities. Excuse me. Thank you. So with that, this is my get off the stage chart. Happy to take some questions. Many thanks to ARMD for giving us a decade of fun. Wish we had a little bit more. Really, of course, this is a lot more than just me or just Langley, but of course, efforts across Armstrong and Glenn and through our prime contractors, ES Aero, and all sorts of other folks.